that we understand how to draw Lewis dot structures, we can actually start talking about the types of bonds that they allow us to see. The first one, and the first actually type of bond we're going to talk about, are metallic bonds. And we won't actually show these using Lewis dot structures, but since it is a type of bond, I think it's important that we look into that. So, in a metal, the outer electrons tend to be very weakly held to the atomic nucleus. And so what happens in a metallic bond is the loose electrons get taken off of the metal atom and actually cause them to be bonded together. When these metal atoms are from different types of metals, it forms an alloy. So an alloy, as we learned last unit, is a mixture of two or more metallic elements. And examples of alloys include steel, brass, and white gold. Now, we spent very little time on that, but it's really kind of simple. We're kind of keeping it simple for the metallic bonding. The second type of bonding that we're going to look at is actually going to have more time spent with it, and that is ionic bonding. Ionic bonding occurs between a metal and a nonmetal, so element on the left side with an element of the right side of the periodic table. It involves a transfer of electrons. One atom gives them up, while the other one accepts them. This is a strong bond. And the cartoon here is actually a little bit of chemistry humor. The figure in the yellow is actually a metal, and the one in the green is a nonmetal, because the metal is actually giving the nonmetal an electron. And you can tell it's a nonmetal because if you look at his name, halogen, that stands for halogen. Alright, ionic bonds are actually therefore created by the electrical force of attraction, this electromagnetic force, which is this attractive force between the positive ion generated by the metal and the negative ion generated by the nonmetal. An example of something that is created between a metal and a nonmetal that forms an ionic bond is sodium and chlorine. What happens in an ionic bond, like I stated, is that the metals lose their electrons to become positively charged, and the nonmetals gain electrons to become negatively charged. So when those positives and negatives attract each other, they come together and form an ionic bond. Now, on your page there, you have some space for an example. But before we actually show you how to write the example in Lewis dot structures, I actually want to show you a little bit what's happening if we were to draw a Bohr diagram. So in this case, we are going to take sodium and chlorine, and these are their Bohr diagrams. So if you look here, the white dots are their nuclei, and then the green dots represent their inner electrons. Now, the one on the left is sodium, the one on the right is chlorine. Now, if you remember, metals lose their electrons and nonmetals gain. Now, we talked about earlier, we want to form that octet rule, and this is a great example of this. With chlorine, we have 1, 2, 3, 4, 5, 6, 7 valence electrons. Now, sodium has that one blue dot, which is its valence electron. So sodium gives up its valence electron to chlorine, which now means that chlorine has 8. We know that chlorine having 8 will be stable. But a lot of times students don't understand how that makes sodium stable by giving away its electron. Well, if you look at that second ring, it has 1, 2, 3, 4, 5, 6, 7, 8 electrons underneath. So by giving away that one electron, it actually exposes that full ring of electrons underneath and actually makes it more stable than if it hung on to that one electron. Now, when I give away that electron, I form a positive ion for sodium, and it gave away 1, so it gets a +1 charge, and chlorine gets a -1 charge. We can also show this with something more complex, like magnesium chloride. In this case, magnesium has 2 valence electrons, and each of my chlorines has 7, just like before. Now, the magnesium is going to take this valence electron and give it to this chlorine, giving it 8, so it is stable. But the magnesium still has this extra valence electron here. So it needs to give to another chlorine atom to give it 8 and make it have a -1 charge. Now, on the magnesium, by giving away those 2, it exposes the full ring underneath, and the magnesium actually ends up with a charge of +2. So, let's look at the example in terms of how we show this using Lewis dot structures. Let's go back to the sodium and chlorine one. Okay, so I have sodium with 1 valence electron and chlorine, which has 7. Okay, to show a transfer, I draw an arrow from the sodium to the chlorine, and that is my first step. I'm actually showing that the sodium is giving up its electron and the chlorine is actually gaining that electron. Now, I can't just do this in one step. I actually have to take it another step. So what I do is, okay, so I put that there. I then put brackets around them. Okay, so this would be in a separate second step. I would draw the sodium symbol without its valence electron with a bracket, and the chlorine symbol with the valence electrons around it, and I just kept mine the same color. They don't have to be different, it's fine. Now, outside of the brackets, I have to put the +1 charge there for the sodium and the -1 charge for chlorine. Now, let me show you another example using that magnesium and the chlorine. Okay. Move that out of the way. Okay, so let's start with magnesium. And we know it has 2 valence electrons. And we start off with a chlorine, which has 7. Okay, draw the arrow here. Okay, that will give this chlorine 8, but my magnesium here is still not stable. So in order to make that better, it needs to give away another electron. And the only way it can give away another electron is if we have another chlorine atom. So now magnesium has given away both of its valence electrons, each to a chlorine. So now we just need to write with the brackets. So we would start off with Mg, and it has a charge of +2 because it gave away both valence electrons. Then I'm going to have 2 of my chlorines, and each of them have a -1 charge. You do have to show both steps, both the arrows piece and the brackets piece, in order to get full credit for anything of those that we do. Now, we do have some more practice that you're going to be working with, but before we do that, let's kind of finish up talking about ionic bonds and some of their properties. Sometimes ionic compounds are called crystals, and that relates to the structure of how the ions are arranged. Ionic crystals and compounds, remember, are formed from elements on opposite sides of the table through ionic bonding. They're called crystals because of the geometric patterns that they form. And this gives us the different types of crystal shapes that we can see. Ionic compounds have high melting points. You can put something like sodium chloride in a pan on your stove on high heat and nothing's going to happen to it. Ionic compounds conduct electricity in liquid, so if we do melt it, or if we dissolve it and it's in a solution, it will conduct electricity. And in general, most ionic compounds dissolve in water. So at this point, what you're going to do is you're actually going to get there's a 2-sided worksheet that one side says ionic bonding, the other says covalent, and there are 5 practice problems. You're actually going to work potentially with a partner or on your own to write the Lewis dot structure showing how this bonding takes place. And then we will review them.